Continuing on with class 11, we're going to go into the next section. We just covered enthalpy. Now we're going to be in section 310. You can't tell because of this silly little volume thingy up here at the top. So in section 310, we're covering the constant volume and constant pressure specific heats, aka CV and CP. So if there's no phase change that is occurring into the substance that we're dealing with, we can start to see a value that we can use to easily get the enthalpy or an internal energy. And this is going to be very useful in many different derivations and coming up with different graphs, the CV and CP. So here they are. I'm going to have to ask in class if you guys have dealt with partial differentials yet. If you haven't, a partial differential, sort of like the idea, a variable can be dependent on a lot of different things. Like it could, for instance, it could be dependent on pressure and it could be dependent on temperature. It could also be dependent on specific volume. All right. But we could take a partial derivative of it, where it means we're just going to take the derivative of one of the things that it's dependent on, ignoring the others. So that's what that means. That's what this symbol is a partial differential, where we're just taking the derivative of internal energy with respect to temperature, with respect to temperature only. And while we're doing that, we're also going to only hold as constant the specific volume. The same thing over here for the constant pressure specific heat, right? We're calling it a specific heat. It's kind of a weird name. I think of it almost as like a slope, if you will, of a graph of internal energy versus temperature, or in this case of enthalpy versus temperature, right? But we're doing the same thing. We're taking the derivative of enthalpy with respect to temperature only as a partial derivative while we keep the pressure constant. And what we can write out for one of our main equations here now, when we have constant specific volume, we can say that Q, right? You know, this is the same equation. Q is going to be equal to U times W, right? And plus, right? Previously, we'd written what U2. Sorry, I'm using my mouse to write, and I'm very bad. Is Q 1 to 2 minus W 1 to 2. But now we're going to say, okay, well, we're just going to say, rewrite the thing, we're just going to say delta, right? Because we're all talking about all these are changes. And then we're going to talk about small changes, right? So just the small changes are going to be equal to this right here. And then they're going to say that, well, that's going to be equal to, so if that's, let's see, I'm looking at these two things. I think that's true. Okay, so this is going to be 0. That's why. For constant volume, that's equal to 0, right? Do you agree? Because work requires volume change, right? Work is going to be pressure times volume change, and the volume change is 0. So that's going to be true. So the amount of heat is going to be equal to du. It's going to be found from CV dt. I already crossed it out. And then with the pressure is constant right here, what we're going to find is we're going to be able to lump these two things together and turn it into enthalpy, right? Because that's the definition of enthalpy, is that du and pressure times volume. But it has to have constant pressure to be able to integrate that, right? Simply, and stick those things together. So you can look these up like in table A5, for instance, and notice that it's going to be at a particular temperature and a particular pressure, right? And there's an asterisk right above this. And what that asterisk means, is what it's going to say, if you see the footnote that goes along with that, is that these values aren't actually constants. We're looking at them as constants, but they are not really constant. But within a certain range, they're constant enough. So this is an approximation. So we have this And you'll also notice there's a subscript O in there. I think it says it in the next slide over, that O is with respect to a zero, it's zeroed out, right? So there's like, we've decided it's going to be zero at like absolute. I think that's what that means. So here's an example of a not quite constant specific heat right out of the this internal energy for the superheated vapor, right? So superheated steam. So he just grabs for 4 pressures and 3 temperatures and plotted the thing out. So I went ahead and plotted it out myself in Excel and plotted them out right there. And you can kind of see that they're kind of all have close to being the same slope right there. Not quite, but kind of. Well, take a look at that. That's the slope right here. And well, this is the CP, so that's kind of a weird one because this should have been the CV. But anyway, it's close to this slope. It ain't great, but it's close, right? So within a certain range, we have a constant slope of this piece right here. Also note that there are specific heats for solids and liquids, and even though we change the pressure maybe up there, we don't need the volume because the volume for a solid pretty much remains constant, especially compared to gases. And also from liquids, it's pretty close to being constant. In fact, in liquids and fluids, we have usually we can assume that it's incompressible, most fluids. Which doesn't mean they're completely incompressible. It means that we can assume it pretty well. Down below, I'm not sure why I have this picture, I'm trying to remember, but these are 3 different ways that we can try to increase the internal energy. There must be a reason for this. I got to look that up. Probably should have looked it up before the video. Whatever. In the book, they wanted to say, oh, here's 3 ways that you could increase the internal energy, either by adding heat, adding work, which ends up being negative when you add work, and or you could add. I guess you're adding work with the electric heater. I guess you're kind of adding power times time, right? So electric is usually going to be current times voltage is equal to, at least in DC, that's going to be the power, and then you do it for amount of time. So you multiply power by time, you get work in. So that's what I guess they're doing right there. All right, so I'm going to continue on with section 311, which discusses this some more. And so this video is probably going to be a little longer because I'm going to add all these things in here. So we have the internal energy, enthalpy, and specific heat of ideal gases. So the ideal gas law, recall, is PV equals RT. All right, this is a volume per PV, MRT if we had capital V, but here we have specific volume. So for an ideal gas, internal energy and enthalpy are functions of temperature only, and so that's like a rule that you can pretty well count on, that they don't really change with this internal energy and enthalpy don't really change all that much with pressure for an ideal gas, and then all gases kind of approach the ideal gas behavior as the pressure approaches 0, also as the temperature goes up. But one thing we need to know is that the specific heat that we're just talked about, it can be a function of temperature, so we have to be kind of careful of that. The 0 pressure, constant pressure, specific heat. So that's what the 0 is supposed to be right there. So that's the specific heat at a 0 pressure is given by that symbol right there. And then the 0 pressure, constant volume, specific heat is given with this. So that's where that 0 comes from and what it means. It's at 0 pressure. And I'm just bringing those 2 important relationships up to the top. The enthalpy is related to internal energy by this right here. Okay, so we've already mentioned this, these 2 things up together. And we could notably replace with the ideal gas this right here, because PV equals RT, so it makes sense that we're putting that in there. But if you change things in small increments, let's just go itty bitty increments of enthalpy, itty bitty increments of internal energy, and it would be the increments of temperature. Of course, the gas constant should be constant. We can substitute this stuff up above, this dH and du, right? So this dH can go weep into there, and this guy can make the loop right over you, right into there. And we notice something, that we have dTs on there, right? We're going to have Cp dt right here. It's going to be equal to Cv dt here, plus R dt. So there's a bunch of dTs. Those dTs cancel out. And now we have this relationship between the specific heats and the gas constant. This is a good one to remember, a necessary one to remember, maybe even one worth memorizing, that the difference between these two specific heats is going to be R. So we could go back up and look into our tables, if we could find it right there, and we could check that out. If we were to subtract this one from that one, we would get this one for steam, right? So I remember all those things. Beep, 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 boop, bop, bop, bang, bah. Oh, I just put it in there. Yeah, there you go. So I already put that in there, right? You could try it out. 1.872 minus 1.410 equals 4.4615. Take my word for it. It does. Here's an interesting thing right here. So there's a graph, and notably we have a constant temperature. And because we have a constant temperature, we also have a constant internal energy and a constant enthalpy, right? Because remember, this is an ideal gas, and it's only dependent on temperature. So if the temperature is constant, internal energy is constant, and enthalpy is constant. So if we go up to a separate line up here where we've just gone up an increment of temperature, we've also got an increment of internal energy and an increment of enthalpy. And interesting happens here. If we go from state 1 to either states 2, 2 prime, or 2 double prime, either way, boom, 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 we actually end up with the same change in temperature, enthalpy, and internal energy. So that's an interesting thing to take a look at. These types of observations are kind of important to us to continually make and to put in our back pocket. So when we go to try to use things, we're going to use some piece of knowledge so we could try to solve a problem. Notably, that this constant temperature is also called isothermal, remember. And an isothermal process is, by the way, also is a polytropic process where the exponent is equal to n equals 1, right? So this isothermal right here, I'm not going to try to write it here with my mouse pen. Or will I? Yeah, I will. Isothermal. I gotta get a tablet for my, no, I don't want isothermal, which is a polytropic with the exponent equal to 1. Remembering that, so therefore PV is equal to a constant. Okay. I don't know if this makes for a good video, but maybe you'll remember it because of that. So specific heats are functions of temperature. That's why we can say this up above. Because of this, and R is a constant, we only need to examine. Oh, this is probably worth making. This is kind of goes on to the other slide. So I don't know why I put it onto this slide. This is information that we need to maintain to be able to continue on with this discussion. Here's a figure, not in our notes, that I added in here out of our book that does show that there is a function of temperature. Right? These things are functions of temperature. The specific heat, and we only need to look at one of them and divide it by R to kind of see how it does change. And R is constant right here, so there is an actual change. But we could kind of draw a straight line in a couple of regions. You can see that's not so easy with with water, right? That straight line, because we're going to treat this as a constant. It should be a flat straight line, and you can see it doesn't work very well. I don't remember what C2H4 is. Seems like I should. Is that a refrigerant? I don't know, probably not. I need to look that up. My ignorance is showing. Look out for these noble gases right here. I think that's what they're called, right? They're noble gases. Yeah, maybe. No, they're these are gases that don't mix with stuff, right? Anyway, but air works fairly decently, and that's important to us because we use that on a lot of engines and stuff. And we use this constant specific heat as a means of doing some estimations. So because do I want to do this now? No. Okay. Well, we'll do that in the next example. All right. So I will keep doing this. Longer video than I meant. All right. So we have some choices how to address the fact that specific heat varies with temperature, and we could take a look at some of them in the next example. So the first choice, and let's just say 1 right here. Can't see it because of that volume thing. We can just go ahead and assume. All right, so we just to treat it like there. All right, so we're just going to make an assumption, and we're going to go. I'll even like the word pretend. We're just going to pretend it is, because well, we need to, in order to talk about different processes. It's going to be a lot easier for us to treat specific heat as if it's constant, even though it's not. You'll see soon we're going to use this K coming up too, which is like the specific heat ratio. That's going to be important to us. Our next choice, and this should say 2 up here, hidden by the volume. We could use table A6 for equations for a specific heat function of temperature. So now, in full disclosure, I've been doing this for years without even recalling. I guess I did know, and I'm not going to say that. But did a lot of calculations based on this right here, and you just have to take the hit for it being a little bit wrong. But you could get better with it by taking this equation form. Notably, instead of temperature, we're using theta, which is to take the temperature in Kelvin and divide it by 1,000. So, and then we have so here's the inputs, these temperatures or temperature ratios, and then here's all the coefficients right here. So we have C1, CO, C1, C2, C3. Now I went ahead and graphed the actuals that I get out of the here's the equations that we're getting, and here is the constant, right? So here's the equation and here's the constant. So you can see that it does vary, and I only went up to like 1,000 degrees, and I think they said, and here, this little asterisk right here will tell you it's only good. This is only good up to about 1,200 degrees, and you can't do anything with it above that. So, yeah, so they get this. There's a little bit of a difference right in here, even up to 1,200 degrees. But there's a lot of a difference, a good amount right here for steam. So a lot of times, basically, you want to use for steam. You're almost always going to use the steam tables, and for air, we can make some estimation, use the specific heats. Also, I did this also for, you can use the tables. And what I should have done, here's the linear approximation for both the internal energy and the enthalpy. And I think I did this for air. Yeah. So you could go up into table A.7.1 and look up the you could look up the properties, right, for different temperatures, right? So it's the same at the same pressure. We're just going to assume it's the same pressure. We only have the table for that, and we can look up the internal energy and the enthalpy, and we can also look up a form of the entropy too, and we'll talk about that later. So anyway, that's the video for these sections where we're talking. What we covered was the internal energy. Excuse me. The specific heats, and then how to account for the fact that they change in temperature. Longer video than I intended. We'll do an example in the next video.